Okay, here we go, more parametrics. Just a quick review. If I have x equals 3t plus 2, and I have y equals, say, sine of t, we can put those two together by simply solving. T equals x minus 2 all over 3 by solving for t. Y equals sine of parenthesis x minus 2 all over 3. And so now we went from having two equations with t as the parameter to one equation, y in terms of x. Now, we can also go back the other way. If I have, say, y equals 3x squared plus 2 to the fourth power. That is an equation of y with respect to x, but it looks as if we have a couple things going on here. We have something raised to the fourth power. So this is kind of one equation going on. So we could say y equals t to the fourth power. And as long as we said that, we could say t equals 3x squared plus 2. Now, instead of taking two equations and putting them together, we're taking one equation and we're breaking it apart. And so you have, in essence, an outer function, the fourth power, and the inner function, whatever's underneath it. Now, unlike these two where there is one equation where they go together, I could actually break this same equation up differently. I could say, well, maybe y equals t plus 2 to the fourth power. So I have the plus 2 and the fourth power, that's taken care of. So obviously, what does t equal? T equals 3x squared. Now you say, well, okay, but that's y in terms of t and t in terms of x. Fair enough, but it's easy enough to say t divided by 3, by dividing both sides by 3, square rooting both sides. And so now I have y equals t plus 2 to the fourth power, and I have x equals the square root of t over 3. So it's simply a matter of choosing what you wish to be. The most basic and simple of all of these would simply be to say the following. If x equals t, then y equals 3t squared plus 2 to the fourth power. All right, ladies and gentlemen, through the magic of television, now we have one more example. If we take our mode and we use our mode to go back to function, we graphed this in function mode. Now, just to show you that it matches, let's go to mode, parametric, and y equals, I've taken this equation and solved it for x, so that now I have a y and an x. So instead of doing this version, let's go up and do the more complicated version. And when we hit graph on this, we should have a graph that looks very, very similar. Yes, very, very similar. So again, regardless whether I graph this or the original or this version, they all should match with your calculator. And again, the kicker there is PAR for parametric mode. Now, that's not the only parameter that we can use in parametrics. There are times where we need to use a different parameter. In that case, we may have to use something with a theta. So, just a moment, we'll do a couple thetas. In this case, what we have is we have two equations again, x equals something, y equals something, but now instead of time, it's in terms of theta. And again, if we take a look at, for example, our moon or our sun example, what we have is we have some objects that's moving in a circular path, and it's going to be based on whatever theta is. Theta at different times, at different angles, is going to create different pieces. And so that's why if we do things in terms of theta, so we have x in terms of theta, y in terms of theta. If we think about it, it's nothing more complicated than if I have a 45, 45, 90 triangle, a x would equal 1, the y would equal 1, while the radius equals root 2. We have y, x, and theta all working together in the same problem. Now, to do this, we can't just simply solve for theta and plug it in, because then we still have a whole mess of x's and y's and thetas. So what we're going to need to do is some way to connect this and this. Well, the best way we know of to connect those two is through cosine squared theta plus sine squared theta equals 1. So the Pythagorean theorem, in terms of trigonometric identities, this is what we're going to use to connect them. So I have this, this, and this. Now, if I could get cosine theta by itself, that would allow me to substitute it in here. So let's divide both sides by 2. So now we have cosine theta equals x over 2. Same thing over here. Let's divide both sides by 4. We have sine theta equals y over 4. So x over 2, the quantity squared, plus y over 4, the quantity squared, equals 1. That brings us to a simplification of x squared over 4 plus y squared over 4, y squared over 16 equals 1, because you square the top, square the bottom, square the top, square the bottom. What we have going on here is an ellipse centered at 0, 0, 4 in each direction in the x, 16 in each direction in the y. And we have that unit right there, all coming from x equals 2 cosine theta, y equals 4 sine theta. So that's using the parameter of theta. We will talk about projectile motion hopefully coming up.